Welcome to today's lecture. During the last 2 weeks, we have been discussing about the fundamental aspects, and at this point of time, we possibly can correlate the occurrence of fluid inclusions in host minerals, and on the basis of the pressure and temperature condition of their entrapment, and also the post entrapment phase changes that we see in the inclusions as occurring combination of different phases like liquid plus vapor or liquid plus vapor plus a solid, and we can correlate the such occurrences to the condition of their entrapment as well as the chemistry of the gross chemistry of the fluid in terms of whether it is a pure water or it is a water plus salt or water plus salt plus gas, and with our basic assumptions that the entrapment was homogeneous, entrapment condition was homogeneous, and the inclusion behaves as a closed system and follows an isochoric path after its entrapment in the host mineral. I would just like to add a little bit of component to the basic understanding of the principles of microthermometry, so that we can correlate the occurrence of the inclusions, and as has been told in many instances, the inclusions that we see dominantly the aqueous biphase occurring as liquid plus vapor, or aqueous polyphase with occurrence of, to put it in a very simple way, a salt crystal maybe of a sodium chloride, which is daughter crystal that precipitated from the inclusion fluid after its entrapment, or it could be a situation in which an inclusion can have an aqueous liquid, a carbonic liquid and a carbonic vapor, which can be explained on the basis of a binary phase relationship between water and carbon dioxide. As we all know that the water, the aqueous component, is also never pure. The aqueous component will invariably have dissolved solid in it, and in most cases the dominant solid is sodium chloride. So, the aqueous carbonic inclusions which we see has the aqueous liquid part and the carbonic part. That means, we know that the inclusion which is occurring like in here, it is an inclusion, it is the aqueous liquid, this is the carbonic liquid, and this is the carbonic vapor. We know that this aqueous liquid will have the dissolved solid in it, and in most cases it will be dominated by NaCl, and so that's the reason why a ternary system like this H2O NaCl and CO2 can be invoked to understand understand the situation in which an aqueous carbonic inclusion will occur, and this system, that is the reason why it is one of the most studied system, with of course we know that there could be other dissolved solids, other chloride species, but they can be always be approximated to be belonging to this simple ternary, which is carbon dioxide, water and NaCl. Although it looks simple, but this is the system on which a lot of work has been done with limited experimental data available, from which some understanding can be made in terms of the entrapment of inclusions. So, what we see here, it sometimes becomes easier to represent the ternary in terms of a binary or a pseudo binary, we can always think of that this is a like the binary which we considered before as water and carbon dioxide. We can say that this water also has fixed concentration of the electrolytes like sodium chloride in terms of weight percent, which can be expressed. So, these two diagrams which have been shown here represents some such kind of a pseudo binary explaining the conditions in which there will be a one phase fluid and the situation pertaining to where the fluid will be splitted up into two different phases as an aqueous liquid plus carbonic liquid. So, if we look at it very simplistically, so diagram 1 and diagram 2. In diagram 1 we see that we see the solvers as we saw before, an asymmetric solvers, and the critical point will be somewhere here, and so this represents the condition in which it will be a two phase situation, an aqueous liquid plus a carbonic liquid, and it will be one phase. And what we see here, that there is also a region of immiscibility. There is also a region of immiscibility which is being generated in a ternary system, and on the second diagram we see that this region of immiscibility is further expanded and it has become a continuous area in which it is a two phase situation. So, situation 1, if we consider that there at a fixed weight percent NaCl, let us say 6 weight percent sodium chloride in the aqueous phase, then if we are considering these two diagrams to be representing fixed weight percent NaCl, then the pressure in case of 1 has to be greater than in case of diagram 2, because the solubility of carbon dioxide in water is a function of pressure. So, with a fixed weight percent sodium chloride, more amount of carbon dioxide could be dissolved, and that is the reason why the immiscibility field is little less compared to the figure 2. Now, if we consider the pressure to be fixed corresponding to one single pressure value, then the weight percent NaCl in case of 1 would be less than that in case of 2. So, that gives us an idea that if with a fixed concentration of water and carbon dioxide, if we increase the sodium chloride content, then the immiscibility also will increase, immiscible area. So, this is something which is very popularly very well known in basic chemistry knowledge. This is the salting out effect, that if we have some amount of salt dissolved in water and we try to dissolve a non electrolyte like carbon dioxide, then the concentration of the salt will fall, or the salt will get out of the system, or it is basically something which you can call as a salting out effect. So, this much of addition. So, this is going to explain. So, we can think of our homogeneous one phase water plus carbon dioxide plus salt fluid, which is a supercritical fluid or could be in its liquid field depending on the pressure temperature that we are considering. So, this the inclusion can be trapped in the host mineral anywhere in this one phase condition, and as the temperature decreases, it splits up into two, and we see them occurring as mixed aqueous carbonic inclusion with salt being present in the aqueous component. And invariably the solubility of the electrolyte like salt like sodium chloride will be very negligible in the liquid carbon dioxide. So, it is the aqueous component which will be accommodating the salt that is there in the system after the splitting or after the post entrapment phase separation. Okay, so, that will somehow that gives us the theoretical framework on which we can understand the entrapment process and correlate the physicochemical the physical parameters like pressure, temperature, and also composition, and the post entrapment phase separation process. So, with this we will now move on to understand the thermal response, the response of inclusions to heating freezing cycles, and we will start with the simple system of water plus sodium chloride. So, before that we would also like to add a little bit to the questions that we posed during the concluding part of the last week's lecture, that how many samples we said that well depending on the nature of the research problem, nature of the top exactly what we are trying to address, depending on different geological environment. It is not a very fixed value that we need to study 100 or 1000 or 5 or 10 samples. And how many inclusions, this also as this particular methodology is very much dependent on the quantum of data. So, the more the better, and here which inclusions, that is the inclusions which whether we would go for the primary or the secondary both, it also depends on the nature of the problem that we are addressing, and what we should do first, and the answer was that we will be doing freezing. We will explain or elaborate on this point, that what will happen if we start heating the samples and try to do homogenization experiments through some illustrations. But there is one question which possibly will come into the mind of the beginners, that which type of inclusions to start with when we begin our microthermometric experiments. Out of the types of inclusions that we have discussed so far, the inclusions which are the pure carbonic inclusions, an inclusion which is occurring as a pure carbonic inclusion where only it is a carbonic either is a monophase or in the form of a biphase. This is liquid CO2, this also liquid CO2, and this is the vapor. So, these inclusions are essentially the easiest one to do the microthermometry, and because we just need to, if they are pure carbon dioxide, or even if this particular liquid carbon dioxide is charged with a variable concentration of methane, then we know that we have to, in order to obtain a homogeneous condition for this particular inclusion, in order to obtain a homogeneous state for this particular inclusion, we may have to just heat it only up to 31.1, and that is the critical temperature of carbon dioxide. And if it happens to contain some amount of methane, the critical temperature will be even less, and if it is not a critical homogenization, then we can get the homogenization temperature anywhere below from minus 56.6 to plus 31.1. So, the sample is not being subjected to any higher temperature, and we also know that if the inclusion is a monophase liquid carbonic inclusion, then by decreasing the temperature by a few degree from room temperature, the vapor phase will nucleate, and we need to just determine at what temperature this particular vapor phase has nucleated, and or vice versa, exactly the temperature at which the homogenization is taking place. So, in a way I would suggest that when we begin our microthermometric experiments after doing routine petrography, and we have got the fluid inclusion fluid inclusion section and fragmented into different chips, well labeling them in terms of the occurrence of the inclusions, what type of inclusions in which area of the fluid inclusion section, and then put the first chip into the stage. Then if the one of the inclusion types to be there in the fluid inclusion section happen to be the pure carbonic inclusion, it is always easy or better to start with them, because another important reason that we need not have to relocate them for any further analysis, because we have got their homogenization condition, and then we can begin our freezing experiments with other type of inclusion, let us say the aqueous biphase inclusions or the aqueous carbonic inclusions. And even the aqueous carbonic inclusions also can be frozen, can be subjected to freezing experiment first, where the where we know that the liquid carbonic component also will have a with a vapor, and we also can get a partial homogenization of this carbonic component, which will come to partial exactly as it happens in a pure carbonic inclusion. We also can get the homogenization of the carbonic liquid part, if the vapor is present, it will also homogenize to either a liquid or vapor. So, these we will illustrate through our examples. Okay, so, now we move on to the response of aqueous biphase inclusions to heating freezing experiment, and we will start with freezing first. This is the diagram which we have already discussed. This is a binary water NaCl diagram, and this is only up to a limited compositional range. So, beyond which we know that it will be a inclusion where there will be solid halite or sodium chloride present along with water, and the such inclusions which are aqueous polyphase inclusions containing a liquid plus vapor plus sodium chloride as a daughter crystal are generally not subjected to freezing experiment, because of the fact that we know already that the liquid is already having the value of room temperature saturation with respect to sodium chloride, and the bulk composition in terms of the sodium chloride content of the total inclusion cannot be determined only by doing the freezing, and which we will discuss later. So, as far as the inclusions which have the sodium chloride weight percent equivalent up to room temperature solubility, means those inclusions which will not have any daughter crystal of sodium chloride in them, they can be subjected to freezing experiments. And if they happen to be on the water rich side, let us say that this star is representing a composition which is on the water rich side, and we will see that what is we are going to freeze this particular inclusion. That means, the temperature is decreased in the apparatus by using liquid nitrogen, and theoretically when this inclusion is being frozen, is being subjected to lower temperature, ice should start forming, should form as and when the temperature is the co-tectic temperature, ice plus liquid coexistence co-tectic temperature is reached. But eventually we will see that the ice will not form at this particular temperature. We need to decrease the temperature far below then corresponding to the temperature of at which the ice is expected to form, or the temperature of eutectic. This is a phenomena which we know as which is known by a phenomena called supercooling, that is many a times required, and there is no fixed value that how much of degree of supercooling will be required for a particular inclusion. It could be pretty variable. For example, if the inclusion is a pure water plus sodium chloride liquid, and the eutectic temperature corresponding to minus 21.2, we may need to freeze it to minus 40, minus 50 or minus 60. It is quite variable, and different inclusions may be needed different degree of supercooling to form the solid. So, once the temperature because the temperature has been decreased to a great extent and the inclusion becomes frozen, becomes totally the content of the inclusion cavity is solidified, then it actually will be a situation from where if this is far below the temperature of eutectic, then what exactly is done is by reversing the process and by slowly warming up that frozen inclusion to gradual higher temperature. So, as we know with increase in the temperature from value far below that of corresponding to eutectic, we will be reaching the temperature of eventually we will be reaching the temperature corresponding to the eutectic. So, once we reach the temperature corresponding to the eutectic, so we apply our basic knowledge of phase relations here. In this eutectic corresponds to two solids, that is ice plus hydrohalite. Hydrohalite is basically sodium chloride and 2 molecules of water, and it is NaCl2H2O, and at this point of time, if we put the temperature on hold at the eutectic temperature, the hydrohalite will melt out. Okay. So, the hydrohalite will melt out, and now it will enter into the ice plus liquid co-tectic. We are warming the inclusion gradually from its sub-zero temperature corresponding to minus 21.2, and then finally the ice will melt here. So, essentially the freezing experiments that we do on these inclusions are essentially in the recording of the phase changes are better done on a reverse route rather than on the direct route, and because of the fact that it will need to be super cooled. So, determining the temperature of formation of ice cannot be recorded, it will only be recorded in the terms of the melting of the ice. For example, when we are increasing the temperature, it moves on the core tectic and reaches the point exactly where it would have intersected the core tectic, and here the solid will melt, and that solid is only ice, because this on this core tectic it is ice plus liquid equilibrium, ice plus liquid coexistence situation. And we can still further even if we heat, bring the inclusion to the original suppose this corresponds to our room temperature, it would always be a good practice to bring it to room temperature, or even we can just record, because here only the temperature that we need to record here is this temperature. So, it is essentially will be the temperature will be the depression in freezing point. This point corresponds to depression in the freezing point, because 0 is here and it is a non-linear curve you can see here. So, this will be, so depending on, as you can make out from 0 almost pure water coming to the eutectic composition of 23.3 weight% NaCl, any bulk composition we think in this area either here or here or here. So, their depression will be more from a pure from 0 degree centigrade corresponding to the melting of pure water, pure ice. Okay. So, our objective is to estimate the salinity of this particular biphase inclusion and express it in terms of weight % NaCl equivalent. And there has been many experiments done by many people, many different laboratories, where the depression in freezing point with variable sodium chloride concentration has been measured, and since this happens to be a non-linear curve, it can be approximated to an equation. So, in a hypothetical NaCl H2O fluid, the solidification of the inclusion fluid will be rapid with rapid cooling, that means the temperature at which it will completely frozen, which you can represent as Tf, will be much less than that of Te corresponding to eutectic temperature in the binary. And now, the interesting situation which we will also be discussing here, we will start that temperature corresponding to eutectic will also be characterized by formation of interstitial liquid in the inclusion which was frozen. So, that is the appearance of the interstitial liquid that actually will be will help us in knowing what is the eutectic temperature, and the final dissolution of the last solid, that is ice or hydrohalide, depending on the NaCl content, that will be recorded as Tm, or even sometimes people designate it as Tm ice. We will list out the abbreviations or the notations that we use in our microthermometric experiments. So, this Tm generally is expressed as the depression from 0 for the eutectic curve left of the eutectic towards the water rich side, means this part, and it suppose it is approximated to a third degree polynomial as alpha phi, beta phi square and zeta phi c phi cube. So, here A, B and C are coefficients which have been worked out, and phi is the depression of freezing point from 0 expressed as positive quantity, means if it happens to be minus 5, it will be 5, or minus 10 will be 10, and this equation has been revised a number of times, and given these coefficients and the value for depression in freezing point, one can always calculate the salinity. So, here it just this sketch is exactly to even though it will be much easier to see them in a video of exactly inclusion undergoing freezing, which one can always see, but this sketch gives a rough idea as to what exactly happens. So, this is our original room temperature aqueous biphase inclusion, this is the liquid, this is vapor, and now this corresponds to the temperature of freezing, the Tf, which is after a substantial supercooling, and the inclusion will be completely frozen. Remembering the fact from our basic phase diagram unary water, where water has the unique property of increasing in volume on becoming on solidification. So, this particular liquid on becoming solidified will undergo expansion, that will cause the vapor to shrink in its volume, because vapor is compressible. So, the vapor bubble will shrink and become deformed. Now, this corresponds to temperature of the eutectic temperature, and you could see that what is marked with this kind of curved line, thick line, is essentially the interstitial liquid. This corresponds to temperature of the eutectic temperature, where this liquid is actually formed by melting of the hydrohalide solid. So, now a situation is here that we have ice plus liquid, and the hydrohalide have just melt. We can hold the temperature there, we can still reproduce it, and that is the temperature, the eutectic temperature in the NaCl H2O system. So, first appearance of interstitial liquid. So, what we need to do optically, we have to get ourselves accustomed to see how the look or how the optical property of this frozen inclusion is changing, because in this case here there will be a good refractive index contrast between the solids, which will be ice, and the liquid, which will be sodium chloride rich. Now, if we take an intermediate temperature somewhere on the cotectic corresponding to this, anywhere on this, it will be represented by this diagram, where we will see the bubble. Now, the bubble has come back to its original size, but not necessarily the spherical shape, and we will have these ice crystals actually floating inside the inclusion cavity in the water. Gradually, the more and more ice is melting, and the water here is becoming more and more diluted with respect to sodium chloride, and this solid ice has got a very unique property. As you can see here, that there is a, initially to start with, we might see some multiple such fragments of this ice, and that all these ice will coalesce to form one mass of ice with a circular outline, and with further increase in temperature on the cotectic, the ice will become smaller and smaller in size, and in addition this ice has also got a unique property that it will get attached to the bubble, and it remains attached to the bubble till it finally disappears and it comes back to the original. You can very well compare that this was our original inclusion, and again after the melting of the inclusion it is exactly the same that we have come back. And because the ice is attached to the bubble, so during the melting of the last ice, the bubble undergoes a movement. Sometimes it becomes a rapid movement in the form of a jerk, and which helps us in actually determining precisely recording the temperature of last ice melting. Now, here there could be many practical things which could be discussed, that what kind of rate of cooling or rate of warming up that we should be doing, what would be good practice. As we know that our heating freezing systems that we are using can have a variation from almost like 0.1 degrees per minute to even 100 degrees per minute kind of rate, and we know that and essentially in any kind of recording of the microthermometric parameters for this kind of inclusions, they need to be this experiment need to be replicated, and the value, say for example in this case, suppose the ice has melted at minus 2.0. So, we need to reproduce it to plus minus 0.1. We would say that in case of if they we need to reproduce the freezing, the last melting temperature of ice to plus minus 0.1, and that only would be well acceptable. So, in order to do that, the rate at which we will be warming when the ice has started to melt, or as the ice has decreased in its size considerably, the less is the warming rate, the better it is, or the better is the possibility that we will be able to reproduce the value exactly. So, so these are the practice. Sometimes we know that the inclusion will become completely frozen at minus 60. So, from room temperature to minus 60 we can go at a faster cooling rate, but we have to again have a very controlled warming rate when the temperature of eutectic would be reaching, so that we know that we will be able to record the exact temperature eutectic without introducing much of error, even though these are all they only come after practice, and this one is just the extension of the considering the binary in a region where it is sodium chloride rich beyond the eutectic composition. So, if the composition is somewhere here, the similar thing will exactly happen. We have to supercool it to a much lower temperature than eutectic, and so here the behavior will be a little different, that up to the point of T E whatever we have discussed will hold good, but here now corresponding to temperature where it is above or just below the temperature of last ice melting, we will get because on this particular cotectic we will have liquid, I mean we have ice plus the situation corresponding to here when the concentration the composition is of higher sodium chloride content than the eutectic composition, then at the eutectic temperature all the ice will melt, and this is corresponding to that kind of a situation, and on further warming all the ice will melt and the solution will become more and more enriched with respect to hydrohalite, and the last solid which will be melting will be hydrohalite in place of ice, as it since it is a sodium chloride rich part of the binary. So, the last solid that will be melting is hydrohalite. So, it has been described in a little exaggerated manner. The hydrohalite crystals will be optically different, as you can see here. There will be clear cut difference in the refractive index between hydrohalite and ice. Hydrohalite will also won't have the tendency to coalesce to form one single crystal. They will be there also they do not get attached to the vapor bubble, and it will not that be very difficult for an experienced fluid inclusion user to understand whether the last solid that is melting, whether it is ice or hydrohalite. So, in this condition compared to the situation where it is a water rich side, the sodium chloride rich side will have hydrohalite as the last solid to be melting. So, that also in that case also when one can calculate the weight percent NaCl equivalent, and by equations which has been like this, a simple equation where the R corresponds to the, because it was worked out in a ternary system of NaCl, KCl and water, and with known parameter of A and B where the psi is temperature in degrees centigrade divided by 100, one can calculate the weight percent if it is a sodium chloride rich. As I have said that if we have a situation corresponding to a polyphase inclusion, water plus liquid water plus vapor plus sodium chloride crystal, then if we freeze that, we will only be able to see the melting of the hydrohalite, and the last the solid crystal will keep on persisting to higher temperature. So, these inclusions which are polyphase inclusion containing halide daughter crystal, they need not be subjected to freezing experiment, and what to do about them we will be discussing in our subsequent lectures. So, we conclude today's discussion on the response of the aqueous biphase inclusion to microthermometric experiments and mainly its freezing. So, we will continue in the next class. Thank you.